Okay, so I'm going to get started. Got some announcements for today. Some of you might have already gotten the PackBack sign-up email. It looks like I've got about 100 participants in the course already on there. But in case you didn't, or if you just want to go through the regular sign-up link, that's now posted in Canvas too. Next week is the first week we're going to try doing everyone posts either 1 question and 2 answers or 3 answers. There's some guidelines that are linked from the sign-up details about what's considered a good question, but the gist of it is we don't want like simple yes or no questions like would this reaction work, would this functional group do something. We're looking for more like open-ended questions like what would happen if you took this reaction and did it to something with an alkyne instead of an alkene, that sort of thing. So there's sort of more in-depth guidelines on the PackBack page, but I figure for now just get signed up, and then next week we can sort of see how people go with sort of getting some questions posted. Okay, and then the Sapling Chapter 14 is now open, and again the sign-up instructions and link are in Canvas as well. And as a reminder there, the due date for Sapling is generally going to be 1 week after I finish covering the chapter that it goes with. So I'm planning on finishing Chapter 14 at some point next week, and when I do that I will set the due date as 1 week after that point. And then I'll remind you guys in lecture too. Also, one last thing is, due to students with accommodations, I need a note taker to volunteer. So if you take notes directly like on an electronic tablet or something, that format is preferred, but paper is okay too as long as you're quick at scanning and emailing it out. So the way this works is you get in touch with me and then I put you in touch with disability services and everything gets arranged through them. And then at the end of the semester they give you a gift card to the CU bookstore, I think is how they're still doing it. But I don't know too many details about it. Anyway, if you're interested and if you're going to be attending lecture consistently, or if you can set up someone to cover for you if you need to miss, this might be a good way for you to get free bookstore swag, I guess. Anyway, get in touch with me and we can set you up. Okay, other questions about that? Okay, cool. Alrighty, so I guess my last of the announcements is hopefully if you guys are checking the course page, my Chapter 14 lecture notes are posted as of a couple days ago. So as a reminder, that's kind of more or less what I'm going to be lecturing from. I'm not going to do it word for word the same as the notes. I tend to do more sentence fragments on the board, and I might just sort of like ad lib like a different description than exactly how I have it in the notes, but more or less between reading the lecture notes if you want to write additional stuff in the margins, but this is kind of what I'm going to be following with when I lecture. Okay. Any questions about that? Okay, cool. Alrighty, so, I guess one other question that people had that I wanted to address is, it sounds like some people who did not see cuprates plus epoxides, we did blow through that topic kind of fast last lecture. The end of Chapter 14 actually kind of does something that is useful and similar to cuprates plus epoxides. So like end of Chapter 14, we're covering another way to make carbon-carbon bonds now. And so I was thinking I might loop back around and maybe tie in cuprates plus epoxides a little more sort of in comparison to the new option that we're going to cover. So maybe take the next week or so, like do a few practice problems of cuprates plus epoxides, like synthesis problems off of old final exams are kind of a good way to start. Like look for synthesis problems that make carbon-carbon bonds from OChem 1 finals. And then do some of those for practice, and then in like a week or so when we're wrapping up Chapter 14, I'm going to sort of tie the new material back into a comparison to the old stuff, so you kind of maybe get like another more, some more exposure to it, and also compare to the new stuff so that you have a feel for like how to tell which one is better to use one, although there's actually a lot of overlap and sometimes either option is good. Okay, questions about that? Cool. All right. So, with that said, just getting straight into Chapter 14 then. All right, so this whole chapter is about reactions of alkynes. Okay, so before we get into reactions we can do with them, we're going to spend a little while on sort of more characteristics of alkynes so that we can explain why they react the way that they do. So a lot of this chapter is actually pretty useful by comparison to the alkene stuff for midway through OChem 1, because alkynes are kind of like alkenes, only more so, is how you can think of it. Okay, so alkynes, we should know, if we know our functional groups, is going to be anything with two carbons that are triple bonded to each other. CC, triple bond. Okay, so we know from early on in OChem 1 that if you've got multiple bonds between atoms, the first bond is sigma and the subsequent bonds are always going to be pi. So that means that this triple bond here has one sigma bond and two pi bonds. Okay, so and we also know that since the carbons are triple bonded to each other and they have like one other thing sticking off either side of the carbon, each of these carbons has two total things that it's attached to, the carbon, like the other carbon, and then whatever the thing out the back of the alkyne is. So each of them has two things it's attached to. Each of them is sp hybridized. Okay. So we can draw sort of a crude orbital diagram of these things. If we show, oh, and I guess to sort of elaborate on this a little bit, each carbon is sp hybridized, which means that each carbon has two leftover or unhybridized p orbitals. And that's what we're going to be using to make the pi bond. You know what, I'm going to pen up just a little bit on the camera here. Okay, cool. All right, so we can sort of show, if we're looking at, say, the simplest possible alkyne with just the two carbons and then an H stuck on each one. The sigma bond between them, we know sigma bonds are always along the line connecting the two nuclei. So the sigma bond here is just sort of like a blob-like orbital in between the carbons. There's actually a couple extra teeny lobes out the front and back of each carbon, but usually we just care about the biggest lobe in between them. So this is the sigma bond. And then we also have two unhybridized p orbitals on each carbon. Turns out those are perpendicular to each other, as p orbitals are. So we can actually show one above and below, like this. So that's one p orbital. And then the other is going to be a little hard to draw, but it's sticking out in front and back of the board. So kind of like this if you're doing perspective. So we got two different p orbitals on each carbon. And then the same thing's going on over here. One p orbital here, above and below, and then one p orbital front and back. Okay, so to make the two pi bonds, what we're going to do is have one pair of p orbitals, say like the vertical ones here, sort of wrap together and join up on top and bottom of the sigma bond. So one pi bond is above and below the sigma. So you're going to have, and it's not going to look great, but like these vertical lobes that are sort of in the plane of the board can merge together to make one pi bond that way. And then you also have one pi bond in front and behind of the sigma. So you also have this thing going on where, all right, this is going to look really weird, but this is sort of like one lobe here is sticking out towards you. And then this lobe here is in back of the board. Okay, so this has sort of two separate pi bonds that are sort of at 90 degrees to each other. So think of it sort of like, I don't know, one of them is kind of like vertical with two parts, and then the other is like 90 degrees to that horizontal with two parts. Okay, so any questions about that? Okay, cool. So we know that each carbon is sp hybridized, which means that the geometry around the carbon is going to be what? Linear, yeah. So, kind of a nitpicky thing, but I guess a way to avoid making your TA or exam grader wince when they look at it is when you're drawing the zigzag structures for these molecules, you want to make sure you have a straight line going to and from the triple bond. So you want to draw it as this. And not as this. Like, I know we're sort of in the habit of doing every consecutive bond is like bent about 60 degrees from the next one when we're doing zigzags, but that's not really correct for a linear geometry atom like our alkynes here. However, so I guess when you've got a linear molecule that's not being like constrained to any particular shape, it's going to relax out into this fully linear geometry. It's not going to just zigzag up by itself. But there is a little bit of flexibility there, as it turns out. If you were to take an alkyne like this and somehow like tie its two end groups back, it can actually put up with a little bit of bond angle bending. So what we're going to look at is cycloalkynes. So we've got some deviation from linear is okay. If you're looking at ring structures. So basically any ring with 9 atoms or larger, like a 9-membered ring or up, can actually hold an alkyne. So in other words, oh, sorry, not 9, 8 actually. Yeah, so 8 and up is okay. Drawing large rings is always a little weird. All right, so 8-membered ring, you sort of draw like a stop sign. Okay, so this actually turns out to have low enough ring strain on the alkyne that you can actually squeeze a triple bond in there. And you can do the same thing for 2, 3, 4, 5, 6, 7, 8, 9. Okay. Something like that, a 9-membered ring. Both of those turn out to be stable enough to isolate. Anything smaller than that, and you're not going to be able to have an alkyne in it. So like a 5 or a 6-membered ring. Are too unstable to isolate as like a permanent structure of a molecule. There is a little bit of evidence for some reactions we're going to see later that it really, really briefly might go through a 6-membered ring with a triple bond for one particular reaction. But you sure wouldn't be able to like trap it and put it in a bottle or anything. It is a very, very brief transient intermediate. Okay, questions about that? Okay, cool. So a little bit more formalism before we get into the good stuff with reactions. Naming these things we're going to look at real quickly too. Okay, so just like always, we've got sort of two systems for naming, either by common non-systematic names or by Iupac. And I think the book calls Iupac substitutive naming. I just like calling the two systems common and Iupac. Okay, so common names are based on acetylene, which is the simplest possible alkyne. So basically, you're going to have an alkyne and one or both of the H's has been pulled off of acetylene and replaced with some kind of R group. So you're just going to name it as like whatever alkyl group acetylene or di whatever alkyl group acetylene. So for example, and I'm going to draw two different ways of showing this. Okay, so like this thing, we've popped one of the H's off, replaced it with a methyl group, and we could just as easily have drawn this as this molecule. We've got a triple bond and then a single bond to the end carbon here. This one would be called methylacetylene. Does the camera see that low? Yeah, looks like it. Okay, so that's methylacetylene. If we did that twice, so we've got both of the H's replaced by methyl groups. This is going to be dimethylacetylene. If we do two different groups, say like a methyl group at one end and then this 2-carbon ethyl group at the other, this one would be ethyl-methyl acetylene. So you just list them in alphabetical order at that point. Okay, so like everything to do with common names, it works pretty great for small, simple R groups, but things get out of hand pretty quick when you start getting into more complicated side chains, which we will pretty soon here. So you might see some of the older names pop up, especially for simpler molecules, but if you learn one system, learn Iupac because it's a lot more versatile. Okay, questions about that? All right, cool. All right. So one other sort of common naming thing that we will see a little bit potentially is more of a substituent name. And that's the Propargyl group. This is basically the same as allyl. But with a triple instead of a double bond. All right, so if you guys remember the allyl group, it's 2 carbons double bonded to each other, and then a 3rd carbon that's all single bonds, like sp3 hybridized, and then whatever the rest of the molecule is. So like if you have a bromine here, this one would be allyl bromide. for example, or you could have whatever like huge rest of the molecule thing here. Propargyl, pretty much the same thing. Just it's a triple bond there. Okay, so that's propargyl bromide. And similar to allyl, even though these are strictly part of the common naming system, they did get grandfathered into Iupac a little bit. So you might sometimes see like allyl named as a substituent in Iupac naming. Propargyl you might occasionally see as a substituent as part of an Iupac name as well. Okay, questions about that? All right, yeah.
Is that an A-P-R-O-P-A?
Yeah. Welcome. Yep. Okay, cool. So that's pretty much all we got to know for common. Pretty limited applications, but they pop up sometimes. Iupac, definitely a lot more useful. And this is actually very similar to how you would name an alkene. So we start numbering from the end closest to the first triple bond, and then and the ending of the name changes to YNE instead of ENE. And then just like for alkenes, if there's a bunch of them, you could call it, instead of diene, triene, tetraene, you could call it diene, triene, tetraene. So let's just do some examples to get a look at this. All right. Okay, so numbering this thing, we're going to start at the end closest to the triple bond. So I'm going to do carbons 1, 2, 3, 4, 5, 6, 7, 8, 9. So nonane is sort of the basic alkane parent that matches the carbon count here. So I'm going to call this as a non-ine. And then just like if this were an alkene, I would need to include a location substituent, a location number for the triple bond starts. And I only need to include the number for the first atom where I encounter the triple bond. So this would be a 2 non-ine. And then if I had any other substituents hanging off of it, I could throw those in at the start of the name, just like always for alkanes and alkenes. Okay, so questions about that one? Okay, cool. Let's look at some substituents. Okay, so for this one again, I'm going to start at the end closest to the triple bond, which means 1, 2, 3, 4, 5, 6. So this is going to be a hexyne, and it's actually a 2-hexyne because alkyne starts at carbon number 2. But here I actually have a couple of substituents hanging off the parent chain at carbon number 5. So I'm going to call this, I guess to break it down a little bit in case you're a little bit rusty, I've got a methyl group at carbon 5. I've got another methyl group at carbon 5. So this is a 5,5 dimethyl. And then 2-hexyne. Okay, questions about either of those ones? Yeah?
Is there a dash between the methyl and the 2?
Yep, yeah, so pretty much as a general rule, anytime you transition from letters to numbers, they should be separated by dashes. So if Yeah, I guess like sometimes I'll run out of space and have to like split it into two different lines, but this one, there should actually be a hyphen there, whether or not it's on one line or not, so, yep. Okay, cool. So one more example with multiple alkynes. This one here. Turns out you're going to hit alkynes at the same place no matter which end you start numbering from. I don't know, let's go from the right for some variety. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so this is decane derivative of some kind. It's got 10 carbons in the chain. So I'm going to call it dec, and then the ending is going to change to, instead of -ine, I've got two of them now. So if you remember back to alkenes, this would have been a decadiene if they were double bonds. So similar here, it's a decadiene. Decadiene. All right. And then again, we need to include location substituents. My alkynes, I encounter them first at carbon 2 and then at carbon 8. So this is a 2,8 decadiene. Okay, notice that I'm being careful to show linear geometry around my alkynes everywhere I draw them. There's no bending coming into or out of the triple bond. Okay. So other questions about this before we move on to alkynes of substituents? Uh-huh. That's okay.
Are you okay if we separate the deca and like, put the numbers in the diagram?
Oh, yeah, good question. Yes, so just like we did for alkenes, deca 2,8 diene is also a very good name for this one as well. Okay. Yeah, I guess usually when there's only one kind of functional group that's part of the parent name, the convention is like throw it out in front. But especially once we start having multiple functional groups, which we will at the top of the next page in the notes, inserting them into the middle of the parent chain sometimes makes it a little bit easier to follow. Okay. So, I guess in OChem 1, we looked a little bit at alkenes as substituents of larger molecules. Okay. So substituents with alkynes. If you guys remember what we did for alkenes here, so if we had, I don't know, some parent chain, I'm not even going to draw what it is, but so I guess the common name for this group would be vinyl. It's just got two carbons double bonded to each other. If we want to turn this into a substituent of some larger molecule, the Iupac name for this group is ethene, but we're going to drop the E and add YL to call this one ethenyl. Similarly, for alkynes, if we got some parent chain here, and we have this molecule that would be on its own ethyne under Iupac. We're going to drop the terminal E from ethyne, and we're going to add il, so ethynyl. So this is a pretty simple case because there's only one possible location for the double or triple bond in either of these groups. If if there's multiple locations, we're going to have to be a little more specific than that. In that point, we would throw a substituent location for the double or triple bond into the group name, and then we'd have to put parentheses around the whole thing so it's clear like this is all one chunk that's hanging off of the parent chain. And as a reminder there for the location number, when we're looking at substituents, carbon number 1 is always the atom at the point of attachment to the parent. Okay, so whatever the parent chain is here that I just drew as a squiggle, carbon number 1 is the one that attaches onto the parent, and carbon number 2 is the next out from there, and so on. Okay. And then we treat substituents with double or triple bonds exactly the same as we treat any other regular substituent. We just alphabetize them following the normal rules. They don't get any special treatment. Okay, so let's look at an example that uses both of these types of groups, one with an alkene, one with an alkyne in it. And I am going to choose this as my parent chain. Note that I'm including an OH group so that I can specifically say this is the parent, this is a principal functional group, this takes priority over everything else in the molecule, so that I can safely know for sure that anything else I throw on here is not going to get priority. It's just a substituent. Okay, so parent chain for this, let me shade this in or highlight or whatever. So the parent chain here is a cyclohexanol. Don't need a location number for that because in cyclohexanol, carbon number 1 is automatically determined to be the one with the OH on it, the principal functional group, as a reminder from chapter 10 there. Okay, numbering, if I go clockwise from here, I'm going to encounter my first substituent at carbon 1, 2, 3, 4. If I go counterclockwise, I hit my first substituent at 2. So I'm going to go counterclockwise because that's better. So numbering is going to look like 1, 2, 3, 4, 5, 6. So I got something hanging off carbon 2. I got something hanging off carbon 4. What are those somethings? All right, so naming these groups. This one here has got 1, 2, 3, 4 carbons. It's some kind of butene. My double bond starts at carbon number 1 of the substituent. So we're going to have multiple different numbering systems, one for the parent itself, and then one for within this group, one for within this group. So it's important to keep these straight. Doing little like boxes or circles around your numbers might help, or doing different colored inks. I tend not to focus on naming problems because, to be honest, they're not as useful as the reaction stuff, but like it might come up in sapling, for example, a little bit just to get the hang of it. Okay, so let's say this is carbon 1, 2, 3, and 4. Let's use circles to keep those straight from the other numbers. This group is a 1-butene molecule, or since it's a substituent of something else, it's a 1-butenyl. Note the parentheses around that holding the whole group together. Okay, meanwhile, over here, I've got carbons 1, 2, and 3. This is a propyne of some sort. It's a 1-propyne. So as a substituent, it's a 1-propynyl. Okay, so that's my two substituents. I got a 1-butenyl and a 1-propynyl. And then I'm just going to throw them into this overall name with the locations of where they attach to the parent. Alphabetizing, which one comes first? Butenyl, yep. So, and as a reminder, once you throw parentheses on there, you stop caring about like any sort of this counts for alphabetizing, this doesn't. As soon as you see parentheses go up, just the very first letter you encounter in that whole chunk determines how you alphabetize this thing. So even if we had like a tert or a sec or something in here, you're still just going to sort it under the first letter. Okay, so butynyl comes first. It's attached at carbon number 2 of the parent. So 2 parentheses 1 butynyl is that group. And then at carbon number 4 of the parent, 4 1 propynyl. And then cyclohexanol is the parent. And note that I don't need to have a hyphen in between the last group and the parent chain here because there's no number separating them. Okay. So I guess in terms of my philosophy of naming, especially now that we're into OChem 2, I will almost certainly not on a test ask you to actually name stuff. It really sucks to grade, to be honest. But going the other direction is kind of likely to come up at least a few times, where I may give you the name of something and say, hey, this molecule does something cool, draw that happening. And so then you would have to convert the name into a reasonable structure before you can actually get started on the chemistry. Okay, questions about that? Okay, cool. So dealing with suffixes where the alkyne and the alcohol are part of the same molecule. These are also pretty similar to alkenes. Okay, so if you remember, this is where we had a molecule parent name that would end with like enol if it was an alkene and an alcohol at the same time, and then we might have to include substituent locations for both of those parts. Similar thing here. So we need a location number for each part of the suffix. Okay. So this thing, the OH is the principal functional group. This takes priority for numbering the parent chain, so this has to be carbon number 1 here. 2, 3, 4, 5. Okay, so this is pent something. We are going to name this as pent, and then the alkene or alkyne comes next. So we're going to have pent-ine, but we need a location number for the ine part, so it's pent-3-ine. Pent-3-ine, and then 1-ol for the alcohol. And just like we did for alkenes, we can pull out the location number for the first of those and throw it at the start of the parent chain. So 3-pentine, 1-ol is also okay. Okay. So questions about that one? Okay, or
How would that naming look if you have like multiple alkynes and like separate?
So then you could call it, say, like penta, 2, 3, 4, or, well, that doesn't work for octet rule, but yeah, penta, like number, triine or something, and then like 1-ol. Yeah, so it works pretty much the same way, just at that point you're going to have multiple numbers like stacked together, and then you can either have those number groups like in the middle of the name or pull them out front. Uh-huh.
It would still be like dipent 3,6, 9, right?
Well, so since the di goes next to the ine, it would be like penta something 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 diine. Let me actually do an example. I'm kind of ad-libbing this, so I may mess it up a little bit, but let's see how we go. Okay. So this thing, for example. Okay, so we got, again, the OH is priority, so 1, 2, 3, 4, 5, 6, 7. I would name this as hepta 3, 5 diine 1 all, I think is the correct place to wedge those numbers in. I guess the other possibility that occurs to me is it might be hept 3, 5 a diine, but I'm pretty sure this way around is right. And then like always, you can pop those 3 and 5 out in front, and that's also an okay way to order it. Okay, other questions about that? Okay, cool. So then it's pretty much following the same rules as alkenes, where the principal functional group here takes priority, and then that's kind of what goes at the very end of the name, and then all the alkenes and alkynes kind of go before that. Okay, so then the last thing that we need to address is kind of an ambiguity, is what if you've got both alkenes and alkynes in the same deal? Moving the camera around. Okay. Okay, so alkenes plus alkynes together. Generally, you're treating these as pretty equivalent to each other. So if you've got a molecule with like both alkenes and alkynes, you want to start numbering at the end closest to where the first pi bond is. But what if you've got something like this, where, I'm going to draw this twice. Okay, so this molecule, no matter which end you start numbering from, you're going to hit a pi bond at the same place for either one. So if I go left, I hit the alkyne at carbon number 2, versus if I go from the right, I hit the alkene at carbon number 2. Okay, so I don't know why they chose to do it this way, but they chose to give the alkene priority if everything else is equal. So this one is actually the correct numbering, which means that you would then call this as a hept something. So hept 2 ene 5 ine is how you would name that. And again, you can pull the first location out in front. Two heptene 5 ine. Okay. So hopefully this is fairly familiar because it's really, really similar to alkenes, with the one exception of where it clashes with actual alkenes themselves. If not, if you want like a little bit more formalism, I think the chapter notes for chapter 4 are where I have most of the rules for alkene naming, and then it pops up again a little bit in chapter 8. Okay, hopefully you saw this in OChem 1 because naming like alkenes and alcohols kind of pops up there. But if it's been a while or if you're a little shaky on it, those are kind of the two chapters where we get reasonably heavy into Iupac naming. Okay. So, how am I on time? Okay, so I'm going to do like one more paragraph out of the notes that's going to set us up to start doing reactions on Wednesday. Okay. So, types of alkynes. There's actually a fairly important distinction between two different options that we have here. One is alkynes where only one of the carbons has an R group on it. So in other words, the other carbon has an H on it. And we can actually draw that H explicitly, or we can just kind of leave it unsaid. These are both two depictions of the same thing. If you remember, we can choose to show or not show any H in the structure explicitly if it's on a carbon. So these are called terminal alkynes. And I guess really I should make that a little bit more generalizable with R being whatever the rest of the molecule is. So they're called terminal because they're out at one end of a chain, like this is the end of the molecule. The other option is internal alkynes that have two different R groups on them. Which makes sense. They're kind of inside or in the middle of the molecule. Okay, so the reactions that we're going to get into next lecture, Markovnikov versus anti-Markovnikov pops up quite a bit there. So I'm going to show all of my reactions on terminal alkynes so that we can actually look at regiochemistry. Okay, so that's just a little bit of descriptive terms that's not really naming. Okay, I'm going to wrap up there for today, and then have a good long weekend, and I'll see you guys on Wednesday.